Welcome to the video overview of the main families of cast iron, S-cast, alloyed, and heat-treated. We have seen that the conventional international standards are ambiguous and not efficient in defining the grades by the minimum properties. This is because there is not a clear difference in the requirements between the quality of the material and the Brenner hardness range allowed for the same material. So for this we propose a reclassification map in order to better define the different processes that in the years have been evolving into the international standard and added without a clear strategy. And for this we consider the two main metrics that are needed by the designer. On the horizontal you see the yield strength, RPO2, and on the vertical coordinate you see the strength ratio, that is the ratio between the ultimate tensile strength and RPO2. And in this way you see how the different families appears, that are different processes in producing spheroidal graphite ion casting materials that are clearly identified and covering a different area of these two main properties. On this second slide you see the same map, but not showing the different processes, showing of course as before the different processes, but instead to write the designation of the material, they are reporting the material quality index that we find in the minimum properties of both the international standards and commercial standards that are on the market. So we can distinguish now the first family, that is the original ferritic perlitic grades, that are ferritic perlitic grades based on the silicon content up from some less than 2% up to 2.8%. This was the normal range of the ferritic grades definition, where the silicon was low for high impact at low temperatures, or at the maximum level of 2.8 to avoid carbides in thinner section, and so on. And this was the first family, very popular, machinable, with a very controlled hardness range. Then, if we consider this base material, ferritic material with this kind of silicon from something about below 2% up to 2.8, and we make a heat treatment by austenitizing in the intercritical range and then quenching into a salt bath to obtain the perferritic structure, that is ferritic perlitic interconnected, because of the high cooling rate into for quenching into the salt bath. So we obtain the IDI, the isothermal ductile ion, which has very uniform properties in different casting sizes of the same casting, and with a very interesting minimum properties as 800 ultimate tensile strength, 480, and 6% elongation in wall thickness between 25 up to 75 millimeters. On the other side, if we consider this basic ion, ferritic ion, and we add with the copper, we obtain the S-cast ferritic perlitic bullite structure that we know very well, that is has many application in the industry, but that has a problem. The problem is that changing the casting thickness, the segregation partner is changing, and so also the Brenner harness on the same casting with different thickness is changing. So this material is popular in the automotive industry with constant uniform casting thickness and with a controlled Brenner-Harness range, as doing the Fiat standard and the Cybodur material trade name. The new entry in the last less than 10 years, they are the high silicon ductile ions. So the high silicon ductile ion mission should be to replace the ferritic perlitic as cast grades, obtaining an equivalent yield strength, only strengthening the ferrite with silicon increase up to 3.5 or even at 4.3%. This material appears very attractive to the designers, but we need to advise that the state of stress that is applied to real casting is not exactly the same that we have in the tensile test. And even if these grades show a very attractive elongation at the fracture, they are very sensitive when the triaxiality state is increasing. And this is given by the low strength ratio they have. Then we have the austemper ductile ion world, the ADI world, where we can distinguish the first grades, the lowest grade, 750, 800 megapascal ultimate tensile strength, that are achieved by intercritical austenitizing and then quenching into the soil bath. These are the most machinable grades. They require significant alloying because we are obliged to use a low intercritical austenitizing temperature, and so we need to achieve quenchability by adding alloying. But these are the most machinable grades of ADI. That day was invented by Dr. Milberger, firstly, then also subject to a patent called MADI, machinable ADI, and these have been at the beginning of the story of the ADI which is machinable after each treatment. And then we have all the family of ADI, say not normal ADI, so with the austenitizing temperature above the critical range, but austempered above also the austeritic nose, so the so-called upper austeritic ADI that arrive up to 1200 megapascal strength, and that they have the best combination of fatigue strength and also impact properties, even at very low temperatures and especially at a high strain rate. These materials are very, very suitable to face design situation at a low temperature and a high strain rate. And then we have the family of austempered ductile iron, austenitizes above the critical range, the eutectoid range, and austempered at the temperature below the perlitic nose. So they are the hardest grade and suitable for gears, for sprockets, and for wear resistant part in general.